Good morning, my digital pathology trailblazers. How are you today? 6 a.m. in Pennsylvania. Are you ready for Digipath Digest? I checked, it's the 26th. So I am opening the chat. If you are there, let me know that you've arrived and where you're tuning in from. I'm in Pennsylvania, 6 a.m. today, and we have a little bit. I hope it was a thought-provoking title. What if AI tool is lying to us? What if AI is not that correct as we want it to be? Which is kind of the question that is in the back of everybody's mind when we are considering using AI algorithms for diagnostics. So we're going to dive into this a little bit today. When you join, let me know where you're tuning in from. I'm going to be soon going to Poland again. So I don't know if I'm going to stop the live streams for vacation or if we're going to continue. Usually in the summer, the attendance is lower than in the less warm months because everybody is going on vacation. But we'll see. Let's see. Let me share my screen with you. And we can start discussing our papers. Actually, we're going to start with something that is more positive than AI lying to us, and something that was just published just because it was July 9th. Let me see. July 9th. Let me know if you hear me well. Let me know if you see everything. And of course, where you're tuning in from. So let's start with real model deployment of a fine-tuned pathology foundation model for lung cancer biomarker detection. I love this one because this is something I was waiting for a long time. And what do I mean? Why was I waiting for this particular paper? I was not waiting for this paper, but I was waiting for this technology or like this application of AI to actually find utility. And what we are discussing in this paper is a clinical trial about I'm going to tell you in a second. Let's see. So this is Nature Medicine, and we have teams from different places, right? We have Gabriele Campanella, and Gabriele Campanella is kind of like famous in the digital pathology space because I'm just double checking not to tell you like the wrong thing, but she was on the paper about multiple instance learning for prostate cancer detection. And it was kind of a pivotal paper in the digital pathology space. So anyway, here we have her on the new paper. Okay, now we have these are people from Mount Sinai, New York, Munich, Germany, Sweden, New York, Syracuse. The thing is that in this paper, what happened is that models, obviously we are training different models for histopathology slides, and then the problem is that okay, so we have hematoxylin and eosin stained tissues, and the computational methods promise tissue preserving diagnostic tools for patients with cancer, right? Tissue preserving is the keyword here. And the problem is that the clinical utility in real-world settings remains unproven. This is always the problem still. And I see new people joining. Let me know where you're tuning in from in the chat. Just say hi in the chat to let me know that you're really here and it's not just numbers on my screen. So in this paper, we want to assess EGFR mutation in lung adenocarcinoma. It depends a rapid, accurate, and cost-effective test that preserve tissue for genomic sequencing. And PCR is done, right? PCR. Well, there are two things: PCR and next gene sequencing. So PCR-based tests, they provide rapid results but reduced accuracy, and compared with next generation sequencing, because next generation sequencing would be like the gold standard, that is very accurate, and the thing I was waiting for is to leverage the computational biomarkers. In this case, it is a modern foundation model that can address these limitations, these tissue preservation limitations. So they assembled a data set of digital lung adenocarcinoma slides, 8,461 slides. That's a pretty big number. And I see even more people joining. Let me know in the chat where you're tuning in from. Because they wanted to develop the computational EGFR biomarker. And I saw a case report like 2 years ago, 3 years ago about this, and I was waiting for the next thing. So what happened here is their fine-tuned open source foundation model did this, was like detected EGFR, and they conducted a prospective silent trial. What is a prospective silent trial? This is when AI or like some digital test is deployed in parallel with standard workflows. Okay, more people joining even. Thank you so much. AI in parallel with standard workflows. So the standard workflow is still happening. Nobody knows. The people who are treating the patients, they don't know that there is like an additional piece of information, and they don't get this additional piece of information. And the goal of this trial is to check, okay, is this good enough? Is this as good as standard of care? And what they achieved here with this biomarker, this digital EGFR, detecting EGFR mutation status from tissue, was that they were able to reduce the number of rapid molecular tests needed by up to 43%. And I'm like, how do you know that you can reduce it by 43%? So what they did, they ran this algorithm on those images, and there's a score, right? A score whether what's the probability of the EGFR mutation. And they set the score. When the score was very high, the likelihood of EGFR mutation being there was very high. So you can skip the PCR. When the score was very low, the likelihood of this mutation being there was very low. So you can skip the PCR. And then if the score was in the middle, go do the PCR and confirm. So in 43% of the cases, the scores were high enough or low enough compared to the threshold. And the threshold was set in a way that that kind of mimicked the clinical workflow. So that's how they proved that they have proven the real world clinical utility of this computational pathology biomarker. And one thing that okay, and we have people joining. Welcome. Thank you so much for joining. Oh, from Indonesia. This is cool. So this is how they have proven it. And I wanted to start on a positive note because we have a few abstracts that are showing us that AI is not always that fantastic. And one of them is the next one that I decided I'm going to choose for you. The utility of automated artificial intelligence assisted digital cytomorphology for bone marrow analysis in diagnostic hemato-oncology. And I look at this one and it says no abstract available. I'm like, why? Why is there no abstract available? There is no abstract available because, well, I think it's because it's a letter to the journal where the authors decided to write a letter, and it was here. That was March, May, right? What they show here is a very important thing to just be aware of, and always have that in mind for these tests until we have enough proof that we can like trust them, like we trust PCR, right? When you do PCR or any other test, there's always a lab validation that you have to go through, even though these methods are well established, right? Our AI methods are semi well established. We're just starting with this, right? So what they did, they have this artificial intelligence assisted digital cytomorphology, and they have an abbreviation for this. Yeah, here, this AI driven automated digital morphology, ADM, is automated digital morphology. So um, we had 328 routine bone marrow smears. And what they did a conventional optical microscopy and automatic digital microscopy, automatic with the algorithm. And they did 500 cells per sample. And then they did statistics. They did something called visual data mining, patient similarity network color coding. So, like color coding patients with similar like characteristics to identify patient cohorts, and the outcome that they were measuring is cellular classification consistency, clinical classification consistency, critical misclassification, and diagnostic conformity. And what they have here is this table, these two tables. So first, on this one, you can exactly see like what cells they were misclassified. So there's diagnosis. This is how the cell looks like, and they look very similar. So I kind of am not surprised that the automated classification had problems. Expert classification and automated classification, and we have this like for different types. Different cells, right? And all the diagnoses are listed here. So marginal zone lymphoma, mantle cell lymphoma, hairy cell leukemia, chronic lymphocytic leukemia, acute myeloid leukemia, and all the different things, right? So here we have the diagnosis. What was the expert classification, and what was the automatic classification? So all of these are mistakes, right? And what were the mistakes? The summary of mistakes is that for this particular diagnosis, number of cases that were incorrect were 9 out of 43. And what were the misclassified cell? So mostly here, atypical lymphocytes was classified as blast, not further classified, not other classified. We had plasma cell also classified as blast, myeloblast, monoblast classified as lymphocyte promyelocyte, lymphoblast as lymphocyte. So they're things that matter, and that's what they showed us in this particular letter to the journal. I don't know why it's a letter to the journal instead of like a publication, but basically they said that you need to pay attention and validate. So this is one of the instances where AI may and we have guests from Germany. Welcome, welcome. I'm glad everything is working fine. If you have just joined, let me know in the chat that you're just joining, and we move on. We move on in the theme of what if AI tool is lying to us. So this one, this one is not lying per se, but the performance decreases. So what happened in this one? By the way, on purpose, I put these earrings for our live streams in case anybody is interested in getting them, because we have them now in the store. So I'm putting a QR code to the store where you can check the type of earrings that we have, and also a couple of other things, and mainly courses. So you can have a look at that. I'm going to leave the code here. You can scan it wherever, whenever, as we move through a few more publications. So lossy DICOM conversion may affect AA performance. So may affect, right? We're not like, it's not a disaster. It's not a disaster, but we have to pay attention, right? So this is a group. This is, what's the paper? Scientific reports, and we have our science reports, a group from Germany, Frankfurt, Oldenburg, mostly Germany. This is a group from Germany. So, many pathology department digitized their glass slides, right? This is what we want. We want the, and I see people are interested in checking out the store. Go ahead. As I talk about this particular one. So we digitize, right? And the problem is that to ensure the long-term accessibility, it is desirable to store in the DICOM format. Like, there is no digital pathology discussion without mentioning DICOM, right? We want a standard. We want to save and actually like create these images in DICOM. But currently what is happening, that scanners initially store the images in vendor-specific formats and only provide DICOM converters, with only a few producing DICOM directly. And this conversion is not lossless. What does that mean? That it loses something. It's not lossless, right? It loses some stuff, some information. And here they were working with the MRXS files. These are files from 3D Histech scanner, 3D Histech, and they had two like ways of making them into DICOM. So they converted these files depicting bladder, ovarian, and prostate tissue into DICOM images using 3D Histech and Sysmex converter. And an open source tool, both using baseline JPEG for the recompression. So we have two things. We have the 3D Histech Sysmex converter, and we have an open source thing. So what happened? What happened when you do that? And if you're just joining, let me know in the chat where you're tuning in from and what time it is for you. So after conversion, when you looked at those images, there was no human perceptible differences. So like for diagnostic purposes, that would not be a problem, right? Because you don't even see the difference. However, these images were not identical, and there were some structure similarity indices of 0.85 to 0.96. So they were not identical. The vendor-specific converter in general achieved higher values. So the one specific for MRXS files, for 3D Histech files, this one was better, but it was not 100%, right? So AI models based on convolutional neural networks and also current foundation models could distinguish between the original and converted images in most cases with an accuracy of 99.5. So they know that an AI model will know which one is compressed, which one is not compressed. And the problem was that already trained AI models showed performance differences between the image formats in 5 out of 64 scenarios. So here, 5 out of 64, there was performance difference, mainly when only little data was used during AI training. So DICOM images are intended for diagnostic use. If we intend to use DICOM for diagnostics, which we do, then we have to develop or reevaluate AI algorithms on this format. But that's kind of like not surprising, that you have to reevaluate or train on different formats. I think that the surprise, or like the message here is, it's not identical, so please check. I don't know if the assumption was that it should be identical. I don't know. But the digital pathology company, the digital pathology community, is committed to DICOM, right? We want to have DICOM, we want to have a standard for those images. So, because we want to ensure interoperability, and so some first AI trainings with converted files did not result in systematically decreased performance. So if you train with these, everything should be okay, but just make sure, or like keep in mind that this is a different format, right? So if you have any questions, anything you want to let me know, put it in the chat. And let's move on to the next one. By the way, if you're just starting your digital pathology journey, then you might want to read digital pathology book, Digital Pathology 101. I wrote this book for those who are starting digital pathology journey, and I'm going to put a QR code here. No, that's not the one. QR code here. This is the digital pathology book. This is a free PDF that you can download through this QR code. Let me go back to full screen. Is it preventing us from seeing it? I think so. So I'm going to take it down for now. But if you're interested, get the book. And we're going to talk about the next one, towards fair decentralized benchmarking of healthcare AI, with the Federated Tumor Segmentation Challenge and Nature Communication. And we have these image analysis challenges, and computational competitions are the standard for benchmarking medical image analysis algorithms. If you have been in the digital pathology space, you probably have heard about the Chameleon Challenge, where the accuracy, or like the performance of algorithms for detection of metastasis in lymph nodes was evaluated. They did it 2 years in a row. I don't know, probably the data set is still there, and I see that people are checking out the store for earrings and for courses, right? Not just beautiful, but also educational. So these competitions are happening, and they typically use small curated test data sets acquired at few centers, right? So that's not the world. They leave a gap to the reality of diverse multi-centric patient data. And this Federated Tumor Segmentation Challenge represents the paradigm for real-world algorithmic performance evaluation. So what does that mean, federated? Federated is that this algorithm can like go to different places where data is available, like to different centers, right? And it's just a an analogy, but you like send the algorithm to learn and bring it back with the weights, with the knowledge. Whereas for the classical way of checking and training is you bring all the data to the algorithm, like you bring the data, but there is only a limited possibility to bring. You can only bring so much data, right? But if you and also privacy concerns prevent many partners from sharing this data. But what can happen, you can send this model to different places, and that's the federated way of training models, and in this case testing models. So there was this competition to benchmark federated learning aggregation algorithms and state-of-the-art segmentation algorithms across multiple international sites. So they compared it using a multi-centric brain tumor data set in realistic federated learning simulations, yielding benefits for adaptive weight aggregation and efficiency gains through client sampling. So what is weight aggregation? This is basically combining model updates and client sampling. So clients would be like the centers, the labs, the hospitals where the data comes from, and you choose them for each round of training. So not the model doesn't train on all of them all the time, but there is something called client sampling to choose it. So this is impressive. They had data distributed internationally across 32 institutions. Like, can you imagine coordinating 32 institutions? I am impressed by this particular aspect of this paper, that they managed to coordinate 32 institutions. If you have, and also, do we have a lot of authors here? Yes. Yes, that's why we have so many authors here. This is the author list. They didn't even like put where those authors are from, because then it would be probably longer, definitely longer than the abstract. Yeah, so federated learning, right? And you can now compare in a federated way. So congratulations on that. What do we have here? We have, last but not least, we have AI in gynecologic or gynecologic. That's the correct pronunciation. Cytology. So yeah, pap smear evaluation. This kind of AI, and this was published in Acta Cytologica, and we have authors from Pittsburgh, PA, Go Pennsylvania, from China, from Massachusetts, and I'm like Zhengzhou, China. I'm sorry for not pronouncing all the cities. Okay, so this is our last paper. Don't go, wait till the end. I'm gonna put the book QR code again, and I'm gonna put one more here if you're interested. This is a specific course that I have on AI. And I wanted to let you know about it because we just updated with my team. We put the edited versions of the 7-part AI series live streams there. So it's very up to date, and it is like the basics to introduce you to AI, and also it has the updated all the live streams, all the papers, all the audio versions of the 7-part AI series. If you have been in our one of these live streams, let me know in the chat that you actually attended. But now we have an edited version, like you can skip all my ramblings, skip all my mistakes because my editor took care of it. So no losing time, just value Path AI Makeover. Have a look at it. It's very affordable. So if you're interested, but you can do that in the meantime. And let's talk about the AI in gynecologic cytology. So cervical cancer, the background is that cervical cancer is the 4th most common cancer, and in women obviously, globally, with highest incidence and mortality identified in less developed and medically underserved areas in the world. Which it's funny because, well, funny, it's like my mind always goes to like different continents than the North American continent when I hear about medically underserved areas. No, I have enough medically underserved areas here in the Appalachian Mountains in Pennsylvania. So it's not, it's across geographies. So the diminishing cytology workforce, unavailability of expert consultation, high volume of pap tests needing manual screening. So the digital pathology world is exploring innovative solutions, right? AI solutions. Can we somehow improve care without the necessary, like without enough people to actually provide this care? So yeah, there are AI algorithms, and they are potentially transforming for traditional cytopathology practice. And I'm going to tell you something after I go through the abstracts, like a real life example in a country. where this is actually deployed at scale. You can guess what country that is and let me know in the chat if you know about like an AI-driven pap smear screening at the national level. So these AI-based systems are relatively new with limited published data on their validation and clinical utility in clinical practice. So this article aims to increase awareness of the availability of such systems, talks about history. So it's a review, right? And development of AI assisted screening platforms. So whoever is considering deploying this in your institution, that's a good one, pretty up to date one to read, to check, okay, what's out there. There are these AI platforms for screening pap tests, how the performance characteristics compare, and also elaborate on technical challenges associated with conducting clinical trials employing this technology. And they discuss considerations about deploying such systems in routine cytopathology practice. Obviously, you have to be digitally enabled. Oh, we're almost done, and I still see people joining. Let me know where you're joining in from. I'm gonna put the store QR code because the course is in the store as well. So if you're interested in the store, let me know. Well, you don't have to let me know. You can just scan the code and check it out for yourself. And you'll find these earrings there and courses. The key message is that these systems are being developed and utilized in cytopathology practices to screen pap tests. And some of them have good performance and some don't have good performance, right? So the main message is you need a judicious review of these systems using evidence-based studies, and this is imperative to promote widespread adoption. So the message of today's episode is and even more people joining at the end. Thank you so much for joining. I know it's early, 6 a.m. That's very early. Let me put the book QR code for you if you are new to digital pathology. This book is going to help you understand the field better. Let me just do this. No, I want myself. The papers, we're done with the papers. Okay, so this is the book, Digital Pathology One-on-One. If you want the paper copy, it's available on Amazon, but you can totally get a PDF for free on the Digital Pathology Place website. You scan the QR code and you get access to it. You have to put your email in, and then I'm gonna send you the link to download. The message today is, and it's not a new message. It's like for any new method, right? Trust but verify, or rather, first verify before you trust. And it kind of, I don't want to say it taps into the fear that we have that it's going to be wrong. It's a fear, but it's a legitimate concern. Let's not call it fear. Let's call it legitimate clinical and scientific concern that if we are trying to introduce any new tools into the science, into the clinical practice specifically, because then it directly affects the diagnosis, then we need to be sure that it works, and or we need to have a way to prove that it works. So thank you so much for joining me. Thank you so much for scanning the codes and checking out the store. The store was a labor of love with my website designer. She's been working with me on the digital pathology place endeavor since the very beginning. So you will see a very comparable design, and it's just so beautiful. I just wanted to share that, like, regardless whether you want to get something from the store or not, but it just looks so beautiful because she like knows what digital pathology place is about, and it's so interesting to work with somebody for so many years. So we started in 2021, and this is when we put up the beautiful website. At the beginning, I was just like trying to do it myself, didn't look too great, but the information got enough traction for me to engage with her. And fun fact, she's my friend from primary school from Poland. She now lives in Spain and also traveled the world and is like a brilliant designer. But we know each other since we were like 5 and we still work together. So just bragging about how beautiful the store is. Thank you so much for joining me. And I